Hi, this is Matt Witmer from Brody Precision, and welcome back to Networking 101. Our second video in the series will be focusing on hardware and the wired side of Ethernet. So if we go back to our OSI model, that first layer is hardware and cabling, and that's what we're going to look at in this section. So the first piece of hardware, and the piece that probably most people think about first, is cabling. And we're going to look at copper first, and then we'll look at fiber optic. So with copper, you have a cable with 4 twisted pairs in it. Cable is specified at a couple different categories. Category 5E is the most common, and it's capable of gigabit Ethernet. It's all you would need for most HVAC applications. Sometimes you'll see specified on a job for Category 6 or Category 6A cable. But from a strictly network capability point of view, Category 5E is all that would be needed for the work that we do. The maximum length for these cables is 328 feet, which is 100 meters. And on each end of the cable, you will have a RJ45 connector, which is a crimp style connector, and it uses 2 different termination variants. So all that matters with these variants is that each end of a single cable is wired with the same variant. Doesn't matter which one you use, as long as every time you make a cable, that individual cable is using the same variant on each end. So with those categories and specifications for cabling that we talked about, those came about because of different needs for the different Ethernet standards that have come about. So if we look back in time a little bit here and look at something like 10 base T, which was 10 megabits per second, that used only 2 of the 4 pairs of wires that are in a standard Ethernet cable, and that used Category 3 cable for it. Then we moved up to fast Ethernet, 100 base TX, that's 100 megabits per second. That still used 2 pairs of wires, but it required Category 5E cabling for it. We moved up again to gigabit Ethernet, which gave us 1,000 megabits per second, or gigabit speeds, and that used 4 pairs of wires as opposed to the previous 2, but it still used the Category 5E cabling. Then we bump up from the gigabit Ethernet to 10 gigabit Ethernet, that's 10G base T. We won't typically see that in any of our applications, but it's good to know that it's there, and the requirement for that is Category 6A cabling. So again, if we look back in time a little bit when it comes to networking, a requirement previously was something called a crossover cable. Because those previous versions of Ethernet standards, 10 base T and 100 base TX, used a single pair of wires for send and receive. If you plugged a cable in from one computer to another computer, say, or your computer to a Jace back in the day, both of those devices would be fighting each other because they both were expecting to send on one pair of wires and receive on one pair of wires. So they'd be both sending on the same wire and receiving on the same wire. So what we would have to do is use something called a crossover cable, which swapped those pairs of wires so that one end was sending on a pair while the other was receiving on that same pair. Modern Ethernet interfaces today do this automatically using a protocol called auto MDI-X. And it's done internally, you don't have to do it, it's done automatically. And the Ethernet interface will sense whether or not it needs to do it. So if you're building your own cables, it's critical that you test them. A $50 tester can save you a ton of time down the road. I've run into jobs where we were troubleshooting problems for weeks and weeks, and it was another person's IT department that was sort of leading things, and it came down to the cable being bad between one switch and another switch. You can get weird intermittent traffic, and you wouldn't expect to test the cable. So always, when you can, if you're making your own cables, test them. A $50 tester will save you a ton of time. And those testers will test for everything that you would need to know if you're making your own cables. It'll test for open wires, shorts, miswiring if you have pairs or cables on the wrong pair. And another good thing to know is something called a link sprinter here, which is a higher end tester, and it's especially useful if you're going into an existing wired up job where Ethernet is already in place, switches are already in place. You can plug something like this in to the wall, and it'll tell you whether or not that jack has internet access, where that cable that is feeding that jack goes to in the switch closet, what switch it's going to, and what switch port it's going to. So now we looked at copper cabling, and we'll look at the fiber optic side of things. For our use cases, fiber optic is typically used specifically for its ability to go longer distances. We're talking you could go potentially 10 kilometers plus with a single fiber run. You also get higher bandwidth capacity. Again, we don't run into that very often. And it's also really good against noise and interference because it's just a glass fiber with light running through it. So you're optically isolated. But with that comes a higher cost. As you can see, you've got a bunch of different parts probably that you're going to have to juggle here, which is something like an SFP module, which gets plugged into a switch in these special SFP ports, which allow you to select the kind of optics that you need for the fiber that you're using. And typically, fiber optic is used for like backhaul on a network, going from floor to floor in a building or from switches to other switches, because it gives you that longer run distance as well as higher bandwidth capability. So now on the network interface side of things, if we move up from the cabling to what we're plugging the cabling into, the network interfaces are what allow our end devices to connect to the network. If you're like me, you've got a whole bunch of network interfaces when you pull up the control panel on your computer. Those network interfaces can be wired, they can be Wi-Fi devices, they can be virtual as well. So if you're using VPNs for different jobs, you'll see a bunch of virtual interfaces in that network connections window as well. To get to this, you just go to your control panel, network and sharing center, and then change adapter settings, and you'll get a window that looks like this in Windows. And from adjacent, you're going to the platform and the TCP/IP configuration. So now we move up again with our hardware, and we move to the switch level of things. But before we get there, the device that came before the switch was what was known as a hub. You may see some of these out there in the wild, potentially, but they're obsolete and you shouldn't use them. And the reason you shouldn't use them is because they essentially were just a repeater. They would take the traffic in from one port and they would spit it out on all the other ports. The switch itself or the hub itself had no smarts at all. It would just spam traffic between one port to all the other ports, which can cause a lot of issues if you accidentally plug network cabling into the wrong place, or you create a loop. You can basically shut down a network with an endless amount of traffic. So if you see a hub, get rid of it, put in a switch, which provides you the same functionality, right? Additional connectivity to a network, but it does it in a little bit of a smarter way. So instead of taking the traffic into one port and spitting it out on every other port, the switch will keep a table of MAC addresses, which is a physical address that gets assigned to each network interface that gets built. And you plug that device into a switch. The switch will say, hey, okay, I know this MAC address is on this port. So when a frame comes in of traffic to the switch and it's destined for a specific MAC address, the switch will look at that destination and forward it to the proper port, and that would be the only place that it forwards the traffic to. So you're not needlessly sending traffic out to a network and to devices that don't need it. For our purposes, 10100 megabit switches are more than enough bandwidth for what we typically see, unless we're talking about something like IP cameras or something along those lines, where depending on the resolution that you're using, you might need higher bandwidth. As you can see, these switches come in a variety of different sizes and shapes and builds. You've got rack mount, you've got DIN rail mount, AC power, DC power, you name it, there's probably an option out there for you. So if we look at switches, there's also a couple of different flavors of them. The first flavor is an unmanaged switch. These are dumb switches. They do nothing more than keep that MAC address table that we talked about on the previous slide. But the nice thing is that they are plug and play, they're cheap, and you don't have to do any configuration to make them work. They come in those same varieties of shapes and sizes as we talked about before, but there's no configuration that needs to be done to make them work. Now if we look at the other flavor of switch, we have a managed switch. This gives you a wide variety of additional features that you can make use of that, depending on your needs, may be very helpful. Things like VLANs or rapid spanning tree, which is what Honeywell uses for the Cyper 30 to get a ring topology, or MRP, which is what Johnson Control uses as their ring protocol on their IP controllers. Most of these switches will let you do the configuration through a web interface or a command line interface, and they also will take an SD card so that you could build up a configuration of how you like your switches set up typically, and pop that SD card into the switch, and the switch will pull the configuration off the SD card and be off and running. Another piece to note on the hardware side of things is power over Ethernet. So what power over Ethernet is exactly what the name implies, right? It's sending power over your Ethernet cable. This is super useful for things like IP cameras or wireless devices. So instead of having to run power to the devices, you're using the Ethernet cabling that you're running to the devices anyways to give them both Ethernet communications and power. Typically this power comes from a switch that is PoE compatible. So these are more expensive switches that have the ability to send the power out to all of their adapters or all their ports. But if you don't have a PoE switch, you could use something like a PoE injector here from Phoenix Contact, the INJ 1000, which will take a non-PoE Ethernet connection in, power in, and then basically combine them together and send them out in a combined fashion so that you get the power over Ethernet on your Ethernet. The next piece of the hardware is routers. So routers give you the ability to route traffic between individual networks. Typically we'll see this when we're routing traffic between a local area network and a wider or a WAN network. So basically between your local area network and the internet. But they also act as a firewall to protect your network from unwanted traffic and hackers from getting in from outside. And they can also do things like VPN access or remote access for you. They do the managing of IP addresses if you're using DHCP, and we'll talk about DHCP and VPNs a little bit later on. But they will also do that DHCP for you and manage it if you choose to use it. And that's everything for Networking 101 in the hardware wired side of things. Thanks.